Hi, welcome to the next video in crystal structure refinement. In this video we'll talk a bit about a molecule that is very interesting. It's 18-annulene. It's actually a data set from my recent publication, and we'll try to refine the structure. Okay, so you can get the data by following the link to the Cambridge database, and then when you download the CIF file and you open it in OLEX, I think you have to you click solve, then you click refine, then solve again, because there will be some error, and then you will finally solve it. So I think solve, refine, solve, something like that. Anyway, I'm going to do the same thing now. I think it's a very good teaching example, and you will see why soon. Solve. Okay, so 18-annulene, that looks like half of the 18-annulene. We have 9 atoms, right? Let's refine. Okay, we refined. Well, let's do it now anisotropically. It doesn't look too bad, it actually looks nice. Now let's add hydrogen atoms, either by clicking here add H or inputting H add, and optimize weights, refine. Let me just add that the data set was of basically, I would say, almost perfect quality. It's a very strong data set. But you can see that even though our model looks quite good, if I input now grow, we can see the full molecule of 18-annulene, which just sits on symmetry element. That's why in the asymmetric unit we have only half of it. I now input fuse to come back to the asymmetric unit. It looks great, but our R factor is pretty bad. It's 14%. So something weird is happening here. So the thing you should note is that you have a lot of electron density peaks in between atoms, but they are not exactly in between atoms. They are not in bonds. We would be happy if they were in between bonds, because that if electron density peaks appear in the bonds, it means that we have quite strong data set that is so strong that we see electron in bonds, right? But they are a bit further away, and you can see that the peaks are quite large. The maximum peak is here, and it's of weight 1.4. Other peaks are quite large too, 0.9, 0.9, 0.8, yeah, so 1.3. So something is happening here, and the thing that is happening is disorder. Now, if you follow these strongest Q peaks, you can see that basically they draw together a similar carbon chain to our main 18-annulene chain here, right? To that fragment of 18-annulene that we have included in the model. So it looks like we have a disorder in which the molecule is kind of rotated. The major component and minor component of disorder are rotated with respect to each other. And let's try to model it now. So what I'm going to do now is to basically get rid of the hydrogen atoms. Oh, oops, accidentally clicked that. OLEX sometimes does it. You click something, but it actually selects something else. So always be careful. I'm going to delete hydrogen atoms. And also when we play with disorder, we're going to, it's always a good idea to name atoms properly. So I'm going to name them 1, 2, 3, 4, 5, 6, 7, 8, and 9. Great. Naming always helps to navigate through the ins file. Okay, now let's again select these, and we want to split them into 2 parts. How do we do that? We have 2 options. Either we select these atoms, these Q peaks, and we assign them as carbon atoms, then we change the numbers that relate them to free variables, right? So doing this to 1, to 1, to 1, then minus to 1, minus to 1, minus to 1, putting them in part 1, in part 2. But there is an easier way to do it in OLEX, and I think in this case it will work well. Nevertheless, it's always a good idea to check the restraints that OLEX inputs after doing it. So toolbox work, and there is a very nice set of disorder tools. So we're going to split these atoms, and at the same time we'll apply some restraints. Let's say we want to apply same restraints. Okay, let's split. And now using shift, if I just use my left mouse button and rotate the mouse, we can rotate it like this. And when I press shift and move the mouse, we move the selection. So I'm going to try to fit it to these electron density peaks to make them lay almost exactly on the top of each other. Okay, I think that will do. Escape. And now I will kill QPix by inputting kill $Q. And now if we go up, we can see how does our input file look like. So we have part 1, order of atoms is mixed, that's what OLEX just does. So we have atoms in part 1 related to the second free variable. We have a starting point 0.75, great. Part 2 is related to 1 minus second free variable. That looks great. What about the restraints? Are the restraints correct? So we want to restrain 1, 2 and 1, 3 distance between both parts to be the same. We don't want to restrain all these distances to be same. Let's say that we are interested kind of in seeing how long are each bond. When bonds are disordered, when bonds are involved in disorder, when the atoms that bonds connect are involved in disorder, I can't speak anymore, sorry, we shouldn't really pay a lot of attention to them because there are a lot of errors related to that. So we shouldn't really discuss them in much detail, but that's the best we can do. So we want to only relate appropriate 1, 2 distance and 1, 3 distance between parts. And that's what successfully OLEX did. But anyway, I always recommend to check what OLEX does. So what we have is, here are our 1, 2 distances. So we have distance carbon 1, carbon 2 related to carbon 1A to A. Then we have here 2, 3, 2, 3, 3, 4, 3, 4, etc. Here we have 1, 3 distances. So we have distance 1, 3, 1, 3. Between parts restrained to be similar. We have 2 and 4. We have 3 and 5, etc. Everything's okay. Now, before we refine it, it's a good idea to add some restraints on displacement parameters. So I'm going to use CMU with default value. CMU works based on proximity in space between atoms, so we want to apply it on all of the atoms at the same time involved in disorder, because we want atoms from part 1 that are not connected to atoms from part 2 to also, let's say, see each other in terms of the CMU restraints. We want to have appropriate displacement parameters between the two parts made similar to each other. CMU, and for RIGU, it doesn't matter whether we select first disorder component, right RIGU, or second disorder right RIGU again, or we just drag over all of them, because that restraints works based on connectivity table. So it will anyway only work on first component separately to the second component. So we can just do drag over them and write RIGU. And I think we can do the refinement now. Okay. The R factor dropped, not extremely, but now let's try to do the anisotropic refinement. Anis, Control R. Yeah, doesn't look bad, R factor dropped. Okay, something's moving. Again, R factor dropped a bit. Not much. Okay, but it doesn't look too bad. If I now click input show P1, we see part 1. Show part 2, we see part 2. They look fine. Again, show part 1, 2. Now we'll see both of them. So what if we now add hydrogen atoms? We can either click here, add H, or input manually H add. And refine, Ctrl R. Look what happened. R factor dropped to less than 5%. Incredible. What's the power of one hand disorder refinement and adding hydrogen atoms? That's why I really like this example. It's a great teaching example. So now if we optimize weights, we have R factor less than 3%. Weights are almost optimized. Great. Okay, now one more thing that is worth to mention with this structure is that battery tells us what's the data to parameter ratio. In this case, it's less than 9. It's 8 point. Is it 73? I think so. So it's not ideal. We would ideally like to have data to parameter ratio larger than 10. And what we did was we had quite a large disorder. We had whole molecule disorder. And we restrained everything, both disorder components anisotropically. And one could argue that because the ratio of the two disorder components is so different, here is 83%, the smaller one is like 16%, so the electron density related to the minor disorder component is very small. So basically fitting too many parameters to not enough real data. We're basically fitting to the noise. So one could say that the minor disorder component could be refined. I'll just kill the cupics. Could be refined isotropically only. Isot to make it isotropic. So look at the R factor now and at the data to parameter ratio and see what happens. Our R factor increased, but not a lot. But you can see that our data to parameter ratio increased from less than 9 to 12. Why did that happen? Because we are now not refining anisotropic displacement parameters. And there are a lot of atoms that have these displacement parameters. So by not refining them, we increased data to parameter ratio because we decreased the number of parameters. We can refine it more, maybe it will converge the weighing scheme. Okay, we're not going to click refine all the time. Okay, so thank you very much. I hope you enjoy this example. I really like this example. You can really learn a lot by doing that. If you want, in your spare time, you can also use this example to try inputting different strengths of the simu restraints or Rigu restraint, or for example delete all the restraints at all and see what is happening. In this particular case, because the data is so good, if we even remove all the restraints, let's do it now. If we remove all the restraints, I think the model will still look good. The bond distances, though, will be a bit worse, because now we kind of lost this coherence between the bond lengths in the first part and the bond lengths in the second part. So let's have a look at the first part, show part 1. What are the bond lengths like? 1.39, 1.4, 1.39, 1.39. And now let's have a look at part 2. 1.36, 1.34, 1.32, 1.36. So we can see that there is quite a significant difference between the first part and the second part, because we eliminated these restraints. And now if we come back, let's go to history, we will come back to the previous refinement. Sorry, probably a bit more further away. Yeah, does it contain restraints? Yeah. We can see by inputting show part 2 what are the distances like. 1.36, 1.35. Oh, actually we didn't that much. So anyway, we can see that by that sometimes if we have very good data, we actually don't need restraints. It still doesn't hurt to put them if they are, with reasonable strength. But in general, it's if we have very good data set, very strong data, sometimes we don't really need to put restraints at all. It's always a good idea to start with restraints, and then you can see whether if you're deleting them, then how does it impact the model. You can experiment with this dataset. It's a very nice dataset to experiment with and learn some new stuff. Possibly if you increase the strength of the same distance restraints, the bonds from the part 1 and part 2 will become more similar to each other. Of course, we are just interested in part 1, right? And also in situations like this, when we have such large occupancy for part 1 and such small occupancy for part 2, again, that would be kind of stupid to discuss the second disorder component, the minor one, because again, it's related to very tiny electron density. So the uncertainty on that is quite large. So we're focusing on the first disorder component. Okay, so to summarize, if you have a very good data, but you see that something is wrong with the refinement, R factors are large, there must be a reason for it. And one of these reasons could be disorder. And I think this example very nicely illustrates that even a structure where, you look at the ellipsoids, everything looks fine, but you actually look at the R factor and think something is wrong. And what was wrong in this case was that disorder was not refined. And it's a beautiful example how, well, you'd say that, well, disorder, it's just some disorder, it probably wouldn't change a lot. It does. In this case, it changes everything. So it's very important to refine disorder and to refine it properly. Thank you very much.